Hi, I'm Jay Puchara, and I'm going to do a demo of our knowledge graph identification project. So this is a project that uses Probabilistic Soft Logic, and it's available on the Links GitHub repo. So you can clone this repository by copying the URL shown. And now we can just git clone the repository. This will take about a second to download. And we've actually set up different branches for each project. So you can see that the first knowledge graph identification experiment presented at the Semantic Web Conference is in the branch ISWC 13. So we're going to check out that branch. And now you'll see there's a different set of files corresponding to that experiment. So if you look at the README, it gives you step-by-step directions on how to run this experiment. So this assumes you have Maven and Java installed, and there are lots of online resources to help you get started with Maven and Java. So we're not going to cover that. We're just going to assume that you have those installed, and then we're going to, all of these commands will automatically set up a lot of the environment for you. So let's open up another window here. And so each of these, there are actually 3 experiments in the paper, and each has its own directory. So we're going to start with the null lazy directory, an experiment. And you'll see there's a command here called fetch dataset, and we can run fetch dataset, and it will download the dataset, extract it, and create a data directory with all of the data that we need to run the experiment. So as you see, running that command downloads and extracts that data. And now we have this data directory which has all of the data we need. So the next step on the list of commands is to build our class path. So you can just copy this command and paste it into your terminal, and assuming Maven is set up correctly, it'll create this file called classpath.out, which will have all the jars that you need to run this experiment. So it's quite a few jars. Okay, so now we're going to compile the code for the experiment. So again, this is fairly straightforward. A Maven compile will compile all of the source files. It'll download all the dependencies and then compile the source files. And hopefully where you are is build success. If you have a build failure, there's usually some explanatory error message, and it's probably due to your class path or your Maven Java setup. So now let's take a look at what this model is actually doing. So we're going to look at the load data file. And let's just make it a little easier to see. Okay, so this is the sort of boilerplate code you might see for loading data in PSL. So we're loading a number of imports. We're going to, we're going to get as an argument to this class where to find our data, and then we're going to open up a data store that uses that particular data location and sets up an H2 database. So this is this line right here. And now we're going to create a model. And so in this model, you'll see, if you looked at the knowledge graph identification lecture, the various predicates that we're familiar with, cat and rel, and then the ontology predicates for subsumption and relational subsumption, mutual exclusion and relational mutual exclusion, inverse, domain, and range. We call it range 2 because that's actually an overloaded term. We have the same entity predicate for entity resolution. And then we have some other predicates which are sort of special use, and you actually won't see them in this particular model, but we're using sort of the same model for consistency. So you can see we also have predicates for each different extractor that NEL has. So general is sort of this umbrella for any small extractors that are sort of one-offs that we include, but the main NEL extractors, CBL, CMC, CPL, the morphological patterns, the structure extractor, these each have their own predicates which allow us to learn weights for that particular source. We're also including the promotions from previous iterations, and we're also including this, this sort of pattern learned confidence that was used in some previous work. Now, we have all these predicates, and I'm going to load them into different partitions. So a partition is a sort of logical structure which holds a particular type of data. So you might have different partitions for different types of data, such as the ontology, the extractions, the entity resolution, which is what we do here. But you should also have different partitions for your training data, your test data. Sometimes if you have, if you're doing weight learning, you want a partition for the training targets versus the data set without the training target. So we're using a partition for the ontology, and right now in the stable version of PSL, what we're using is a very simple way of specifying partitions. You just make up a number, and you have to consistently use that same number across your code. So when you see these numbers, we're sort of using easy to remember numbers, which we're going to use throughout the code. So we're loading the ontology, we're loading seeds, which are sort of the human annotated facts that NEL starts its method with. We load the entity resolution atoms, we load training data, we load the candidates, and you can see we're loading candidates for each of these extractors. And you'll notice here we're not actually we're not loading the data right here. What we're doing is creating a map, and the map has as its key a predicate, and as its value where to find that data. And this is actually a utility method because we're loading lots of data to make the code a little cleaner. So let's look quickly at what that data loading code looks like. And you can see we have this nice utils class which has a similar structure where we have a lot of imports. And so this is the load predicate atoms, which gets the data store, a map, and the target partition. And it's very simple. It just looks up the file name in the map for the particular predicate. So I guess we're iterating over predicates. It's going to print a status message saying this is the file we're loading, and then it's going to get an inserter from the data store for that predicate and that target partition, and load into it the file that we've defined. So this is the code to get an inserter for a particular predicate and partition, and this is the map entry for that predicate, which is corresponds to a file to load. And you'll notice we have two different helper methods. One is load predicate atoms, and the other is load predicate atoms with value. There's a slightly different inserter that we use for loading something, loading a predicate which has a truth value defined. So that's why we have these two different methods. And you can see the difference in the inserters is this is load delimited data truth, and this one is just load delimited data. Okay, so let's get back to the data loading. So we've loaded the entity resolution atoms, the training data, candidates from each of the extractors. We also load the candidates without any source information into this particular partition, just so that we can see the effect of having the extractors. And now we've loaded all of the different data we're going to need for our experiment, and we have a little message which tells us how long it took. So we're going to run this command. And so here in the README, you can see the command we're going to run. Let's clear the screen, run that command. And so this will actually take a couple of minutes on my laptop. So let's look a little bit at the next step, which is going to be running our model. So let's go to Emacs again and look at what running the model will do. Okay, so these are the imports, and we'll go to the very bottom. This is the main loop. So first, what you'll notice is that we define a weight map. Well, I guess the very first thing we do is actually load the data store, which is the same data store that we have, or the same path that we have from the load data method. Notice that this argument is false. That means don't delete the existing database, use the one that's already there. So we can split up the loading data and the model testing. And this is really nice because you only have to load the data once, and then you can play with your model, change things around, and use the same database. So that false says don't delete the database. So as I was saying, we define a bunch of weights, and these are weights for each of the different rules and extractors. And so if you go back and you look at the model that we're going to define, each of them uses a particular weight that corresponds to the rule. And so those weights are coming from this map that we're defining at the very beginning. And these weights are actually learned from a different experiment that we do. It's actually very difficult to learn weights in this particular setting, so we're using weights that we've learned in an easier setting to do this nel inference. So we're going to load the weights, and we're just going to add that to the model setting. Then you'll see in the next experiment the model settings are a little bit more interesting. So we're going to create a model, and the model settings are the weights. So let's go look at what happens when we create this model. Okay, so we're going to create the model. We're getting the data store and some settings, and we create a new PSL model, and we load the weight map. We have some sort of toggles here in the code that we can use to play around with how the experiment runs. But these rules, you can see the m.add rule syntax is just what we use to create a new rule. These rules look hopefully very similar to the ones that you've seen in the knowledge graph identification lecture. So this says if A and B are the same entity and A has label or category is what we're using here, C, then B should also have category C. And we're going to square the potential. So in PSL, the objective term that phi can either have a linear value or a quadratic value, and we've found in many cases the quadratic potentials perform better. So we're going to say the squared potentials are true. That's something that we defined right up here, but we can easily change these to false to understand how squaring the potential changes the performance. The next thing we do is we define a weight, and as I said, we loaded that weight map at the very beginning with different weights, which we learned from the non-lazy experiment, which was an easier setting. So in this case, the weights are just given to us, but in the next experiment, we'll see how we learn weights. And so these are some entity resolution rules. So this block is entity resolution rules. This block of rules is the ontology. And now we're going to add rules for each of the different sources and seeds. So in this case, we have positive seeds and negative seeds. So negative seeds are things that are not true. So for the positive seeds, we say that that seed implies that the actual fact is in the knowledge base. Same for the relations and labels. And for negative seeds, we say that that label is not in the knowledge base, or that relation is not in the knowledge base. And then for each of the different sources, we have a pair of rules for labels and relations. And each of them has a weight, and that weight is specific to that extractor, and we've learned those weights in a different experiment, as I've said. So you can see here there are a number of these different rules, one for each of the extractors. And finally, at the end here, what we have is a prior. And the prior says that without any evidence, a particular category or label fact and a particular relation fact is unlikely to be true. So we give this a small weight, and that weight prevents everything from being true, and it pushes down the truth values in the knowledge base without any other evidence. Finally, what we do is we print out the model. So if you're running this on your terminal, you'll see, or you're running the experiment and redirecting the output, you'll be able to look back and see exactly what model was created and what the weights were. And then we return the model to our main setting. So this is where this model comes from. Next, we're going to run inference. And in inference, we're going to infer the values of all of the different facts in the knowledge base. And so we have some settings that we set up. And again, this is just to allow us to easily try different combinations of rules or different features in our model and understand how they affect the outcome. So we're going to pass those inference settings. So running inference is much less code. Now what we do is we create a dummy partition that's empty. And this is so that when we try to throw out a particular feature, as we do with the different inference settings, we just load empty data instead of loading the data that we've loaded. So we define these partitions. Ontology is either going to be the partition that we previously defined in load data if use ontology is true, and if use ontology is false, it's going to be the dummy partition. The seeds, we don't have a particular inference setting for that at this time. Entity resolution is similar to the ontology. If it's true, then we use the partition we defined in load data, and if it's false, we use the dummy partition. In this case, we're not actually using the training data for weight learning, so we're going to load that as a partition. Use sources are different extractors, and if we're going to use the extractor source as a different as a factor that allows us to use different weights, we'll load all of the sources. If we're not going to use sources, we're going to load all the data that's in one big partition without any differentiation between sources. Finally, we define a partition to write our results into. So this is where all of our output is going to go. And then we output a nice little message which says that we're going to start inference. So we load the settings we need for the inference, and we add two properties. One is setting the maximum number of iterations to 30,000, which is a very large number, just in case the optimization problem doesn't converge. And I believe we don't ever hit that number, or if we do, it's rare. And then the next setting we add is the maximum number of rounds of iteration. So this is a good time to talk about lazy inference. So what we're going to do is called lazy inference. And what lazy inference does is it runs the model using whatever rules are true with the data available. So you might have some small set of rules or small set of facts which are interesting to PSL because they're supported by the evidence that you have. So you might have you might see a noisy extraction which says that the Giants play baseball. And so you'll infer the values of all of the facts using the extractions you have at hand, maybe for example, that the Giants play baseball. Now, you might have a set of new facts which are now interesting. So for example, if the Giants play baseball, there may be a rule which links playing baseball to the leagues, the American League or the National League. So those facts might now be interesting to our reasoning inference. And what lazy activation will do is look for anything which is supported by a truth value over a threshold. In this case, the threshold is 0.01. And anything that has a truth value higher than 0.01, it'll add to the list of things that it's going to infer a value for. So in each round, it infers values for all of the facts that are supported by evidence. And then it looks for new facts that are supported as a result of the inferences it's made and repeats the process. So we set the maximum number of times this process repeats. We found 14 to be the right number for this problem. You could set it very high, you could set it low, and have a faster inference. Okay. So the next thing we're going to do is list a set of closed predicates. So these are the ones whose values will not be inferred. And so we basically close everything except for cat and rel, which are the output predicates for facts in the knowledge graph. Everything else is treated as an observation. So any predicate that you have that's treated as an observation should be a closed predicate. Okay, so now we start inference. And we set the time, and we get a database. So this database has the right partition that we specified for our results. The next argument is the set of closed predicates, and then all of the subsequent arguments are read partitions that we use as observations. So again, the structure is output, closed predicates, observations. And so we define the database we're going to use for inference. And then we do lazy inference. We specify the model, the database, and then the configuration options, which again were the number of rounds and the number of iterations. Okay. So finally, to run inference, we just take this MPE object that we defined and run MPE inference. Okay. And last, we close the database, which deletes all of the temporary structures in memory and releases that and makes sure that all of the values are committed to the database. And then we tell the user that the inference is complete. So we also print the results, which are everything that's in the right partition, as well as the seeds, because the seeds are actually overlap a little bit with the training data, with the evaluation data. So we print all of that out, and then we talk about how long it took to run this. So I believe print results is actually in our utils. Is that correct? No. No, there it is. So print results is actually very simple. It just looks for, it creates a dummy partition because whenever you create a database, you need a right partition. So it uses this dummy partition as the right partition, and the read partition is the one with the results you want to print out. And then we create this printer object, and it gets all of the atoms which have the predicate rel and prints them out. And then it gets all of the atoms with the predicate cat and it prints them out. And then it closes that database that it created for the purpose of printing results. So that's this helper method that we've created just to print results. And you could also put this in your utils class. In this case, since we're specifying the predicates in line, that's probably why I put it in this run KGI class. Okay, so now that we've looked at the model, our data loading has finished. It took about 5 minutes, so it's good that we spent some time talking about the model. We can run this model. Actually, so the lazy model, as I said, it infers the whole knowledge graph. It has this spreading pattern of activation, so every time you learn a fact, you start thinking about new facts. And so it does take a fair amount of memory, and it does take about a couple of hours on a good server, so that probably means that on my little MacBook Air, it'll probably take 4 or 5 hours and really slow things down. So I'm just going to run the script and kill it right away just to show you that it runs and prints the model. So it's redirecting output to this file out, and let's quickly tail out. No. Or let's actually look it out. So as you see, it read the rules and prints the model with the weights, and then it says it's starting inference, and it'll give you some warning messages for values that are, for the fact that some of the values it's using a default. And now it'll tell you, again, it has some warning message about default options it's using. And now it'll tell you how many instances of the rule it's grounded. So in this case, there are 1169 instances of this same entity rule. And it'll sort of go on. And so this is just the grounding, and then it'll run inference, and then it'll use those results to ground even more rules and repeat that 14 times before it completes. So let's not wait the hours necessary for that. But that gives you an idea of the straightforward case where you're inferring the full knowledge graph. We're going to look at a slightly different case now, where you're actually only looking at part of the knowledge graph that you specify. So again, what we're going to do is fetch the data set for this problem. Okay, data set's there. Next thing we need to do is build our class path. To compile the code. And we're going to load the data. So let's look at this model now, and as I said, it's slightly different. So hopefully you'll see a slightly different set of rules and an interesting set of techniques used for this problem. So the big difference you'll see in this model is that for each of the rules, we have this predicate valcat. And valcat says that we should only ground this rule if we believe this category or this potential fact is one that we care about. So in this case, what this experiment is doing is it's predicting values for a two-hop neighborhood or a restricted two-hop neighborhood around the test set. And so we don't want to think about any fact that isn't in that two-hop neighborhood around the test set. And if you don't, so if you do lazy inference, it'll start adding new facts, even ones that you don't care about. So you don't do lazy inference in this case. You're doing sort of the normal inference. And in the normal PSL inference, you actually specify each target that you want to infer a value for. And if you have a rule which has evidence for something that's not in that target set, PS will throw an error and complain, and your model won't run. So in this case, if you want to write this sort of model where you've specified all of your targets and you don't want PSL to be upset if something that isn't in your target set is supported by the evidence, you have to scope your rules to only include the targets that you want to infer. And that's exactly what we do here. We add a new predicate, valcat, and valcat says, you know, category BC is something we want to think about. Or in this case, valrel says this relationship BZR is something that we want to think about. So when this rule implies that BZR is true, if valrel is true, then that means that it's going to be inferred. And if valrel is false, this rule will be trivially satisfied, and PSL will not try to infer a value for this particular atom. And so we do this for all of the rules here. And as I said, this is the main difference between the lazy and non-lazy approaches. So at the bottom here, you'll see that we have very similar code for everything that's in inference. The difference, another difference in this experiment is that we're going to learn weights. So the other PSL videos in the channel will probably talk a little bit more about weight learning, but I'll go over it quickly here. So again, we set up all the partitions that we need. In this case, you'll see that we also have a set of targets for training and a set of targets for testing. And as I said, we need to have these targets in order for us to use the normal PSL inference, where we actually have to specify all of the atoms whose values we're interested in. So these targets are going to be loaded with the values we're interested in. Okay, so now you'll see we have a lot of different write partitions. There's a write partition for the training data. There's a write partition for the weight learning data. There's a write partition for testing, and there's a write partition for our observations at inference time. So let's go over, I think hopefully they're all used. Let's go over what each of them means. So the first thing we do when we want to run weight learning is that we condition on the training data and infer the value of all of the targets. So what that means is that we treat the training data as observations, and then we specify a set of targets, which are atoms whose values we want to know, and then we infer the value of all those atoms using the training data as an observation. So we set up the sort of normal variables for creating a database, and so you'll see in write_in_tr, which is the write partition for inference using the training data, we close all of the predicates except for cat and rel, and then we condition on all of this data. Note that includes the training data, and it also includes the targets for the training data. So these are the valcats and valrels, which allow us to ground only a subset of the rules. And then we run inference as we did in the lazy inference case, except instead of creating a lazy MP inference, we're just creating MP inference. And again, this is because we've specified all of the targets, and we're not going to let PSL figure out what it needs to ground. Okay, and then we'll finish inference for that training data. Okay, now the next thing we need to do is infer values without the training data. So what we're going to do is close the predicates rel and cat here, and these are the things we inferred using the training data. So now we're going to treat those as observations. We're going to treat the predicates that or the atoms we inferred using the training data as observations whose values we want to match by changing our weights. Okay, so just to repeat that, what we're going to do is try and match the values we got using the training data just by changing the weights of the rules and not using the training data. Okay, so we're going to create a new set of configurations here, and you'll see these configurations include some for weight learning for the voted perceptron algorithm. We're going to create two different databases. This one is for weight learning, writing out the results of weight learning, and you'll see that we don't condition on the training data at all here. So this is just the candidates and the ontology, the seed data, and again the train targets just to scope what's a valid output. And the second database we create uses the training data as well as the atoms that we predicted or inferred using the training data. So this write_in_tr, remember, is the partition that we used in the previous inference to learn the values or to infer the values of all of the atoms using the training data. So in this case, we're conditioning on that data. We're closing cat and rel. So in this case, what we have is a database which uses all of the atoms that we inferred with the training data. And what we want to do is to get this observations DB, the one which knows all of the values using the training data. What we want to do is to have the weight learning DB, the output of the weight learning DB, match this observations DB. Okay, so this is how we set up a weight learning DB and a observations DB, and then we try to run weight learning, and there are a number of different weight learning algorithms. We're using max likelihood with MP inference, and we specify first this random variables DB. This is the one where the output of weight learning will go with the learned weights, and the observations DB, which again is the database where we've inferred all of the values using the training data. And again, we want this DB's output to match this DB's output, and we're going to adjust the weights to make that happen. Okay, so the way we learn is we just call we set up this voted perceptron learner, and then we call vp.learn. And then finally we close the databases, and weight learning will be complete, and we'll print out the model it learned. And really what that will be is all of the rules that we've defined with weights learned using the training data. Finally, what we're going to do is run inference on the actual test data. So these are the test targets, the 2-hop neighborhood around the test data, and we're going to run inference on that test data, and then compare that with our evaluation set. So this is pretty straightforward. It's just like the example in lazy inference, except it's non-lazy inference. So we set up a write partition for the output of our inference. We close all predicates except for cat and rel, and then we condition on everything. In this case, we specified the test targets, which scope which values we're interested in this 2-hop neighborhood, and we also condition on the training data here because there's no overlap between the training and test data, and we can use it as a signal to help us infer the value of the test data. So we define an MPE inference with the model, this database that we've created, and the inference settings. We run inference, and then we say inference is complete and print out the results. And then we also specify how much time it took for each of these steps. Okay, so this is sort of the full end-to-end KGI application on a small test set. And one of the nice things is that this runs extremely quickly, so we'll go through and just watch it do all of the steps here. Okay, so we've loaded all the data. Again, it took around 5 minutes. Let's go to the README and run this, and let's just let's get this set. Okay, so KGI, and let's tail the file. And so it read the rules. It's warning us that it's using some default values. It's grounding rules against the database. And this is the first inference. This is the inference that uses the training data and tries to infer all of the targets for that training data. You can see it's running, the residuals are decreasing, so it's getting closer and closer to satisfaction, and the optimization completed in just under 500 iterations. Now it's going to start weight learning. Again, it's saying what the options are and what default options it's using. And it'll take just a minute for weight learning to get started and start running. Okay, and so what it's going to do is, again, ground a number of rules. This is to do the inference for the weight learning output, not using the training data. And then it'll run that inference for the weight learning output and try to optimize the model. And then it'll look at the difference between the model that doesn't include the training data against the model that includes the training data, and try to get them to match by taking the number of steps for each of the rules. And so you can see here what it's doing is just taking steps for each rule, which is probably going by a little fast, but if you're looking at your own screen and running this, hopefully you get a sense of what this looks like. So it has sort of an expected incompatibility, the true incompatibility, and then it takes a step based on that. So a step of this and the expected incompatibility and the truth incompatibility. Okay. So this will run a couple of minutes. The weight learning is a little slower than the inference on the test set. So let's talk about what we're going to do next. So one thing we want to do is run to look at how well our model does. And so we have a script that looks at the AUC, the F1 for the cat facts and the rel facts against this data set that's been created by Shangpu Zhang and his co-authors for NEL, and it's sort of a manually labeled test set with thousands of cats and rels that have been labeled. And so once we do that, we'll look at the results, and the next thing we'll do is we'll add some rules that are a little bit more complicated than the ones we've included so far, and look at how much better things get. And so it looks like it's finished. And so here you see the inference took 25 seconds, the weight learning took 40 seconds, and then the test set, it took just under 20 seconds to run inference on the test set. So this was actually the fastest part. Learning the weights was a little bit slower, but you only really need to learn the weights once, and then you can use that learned model as many times as necessary with different inputs. So let's look at what weights it learned. So here you can see these are the learned weights for each of the rules. You can see some of these are more reliable than others. And so they have higher weights, others have lower weights. Okay. And now if you look at sort of the end of the file, we have a bunch of different outputs. And it's using these numbers here because these are actually PSL assigns the arguments of the predicate unique identifier, so it's easy to look them up, to do joins when it's grounding rules. So having the actual string that we see in NEL would make it very slow. But if you look in the data directory, we have a little file called names.txt, which just maps each unique identifier to the value that NEL uses. So this is a large file because NEL has, for example, latitude and longitude, but this allows us to very quickly run these models. Okay, so our output is done. We have the command to test, to look at the output to test this against our evaluation set. So let's just run that command. And so here you'll see the same results that we've reported in our papers. It's AUC close to 905, and the F1 sort of peaks at 0.55 at 0.854. And you can see how the recall sort of drops as we increase the truth value threshold, and the precision increases as well. So this little utility will help us understand how the model is doing, and if we tweak the model, we can look at whether it changes the distribution of precision and recall across thresholds, whether, for example, it helps us infer relations or categories, whichever different rules might have different impacts. So let's add a couple of rules to our model, recompile it, and run it again and see what happens. So the rules I want to add are sort of interesting. I like to think of them as transitivity rules, or sort of these patterns. So I sort of wrote these out ahead of time just to save time in the demo, but you can see we have these unique identifiers which were in that names.txt file for the different relations: athlete plays for team, team plays in league, and athlete plays in league. And so if you think of these three relations, there's this neat relationship where if an athlete plays in a league and the athlete plays for a team, then it's likely, if an athlete plays for a team and the team plays in a league, then the athlete plays in that league. And we add this valrel to say we're scoping the output. So if we know which team an athlete plays for, and we know which league a team plays for, then we know which league the athlete plays for. And so you might have a lot of facts about which teams play in a league, and you might have a lot of facts about which athlete plays for the team, but you might not have that many facts that actually associate an athlete with a particular league. So maybe this is a good rule to have because it fills this hole that you might otherwise have. And it's very straightforward to write this rule in PSL, but it can actually help us fill out our knowledge base. The second rule we have is that if a team has a particular home stadium and that stadium is located in a particular city, then the team plays in the city. And again, you might know from a lot of news articles what stadium the team was in. And you might have locational information about the stadium by scraping the stadium page about what city it's in, but maybe you don't see as many mentions of the team in the city. So you want to add a rule like this to fill that gap. So these are some new rules, and we're going to copy this those rules, and then we're going to go to our run KGI model and go to where we've defined all these rules, and we're going to add these new rules. And then save our model. Now we'll go back to this directory and run maven compile to update the classes to use this new rule. And what we're looking for is build success. Great. And now we'll run the model as we did before. We don't have to load the data again because the data is the same between the model we had before and this model. It's exactly the same candidates, it's exactly the same targets. Really all we wanted to do is change the model. And as I said, you don't have to pay that 5 minutes to load the data each time into a database. That data is fine. All you really need to do is change your model and run inference again. So in this case, we're going to be running weight learning again, and that took about 3 minutes just because we added new rules and we want to see how good those rules are. So it'll take, again, about 3 minutes while this demo runs. And so we'll just look at these rules again. And as I said, PSL doesn't really understand the strings if you define the rule in terms of these unique IDs, and the way you get these unique IDs is you tell your data store, give me this unique ID, and you specify the unique ID, and then I've named them sort of the text equivalent just so it's easier to read these rules. Let's just clean up a bit. I guess while we're waiting, one more thing we can look at is loading the data in the non-lazy case. And actually, it's very similar. The only difference is that we have we define a number of these different maps for the inference targets. So we have maps for training, we have maps for testing. We found when we were testing actually that there were things in the test set which were not included in the neighborhood supplied by Shankui Zhang in his paper, so we just added the things that were in the test set, which is why we have this one additional file. Again, we have the same thing defined for inference. Okay. Let's take a look at, so we're finishing up weight learning. Maybe look at this output while we're waiting as well. So let's look for our new rule and see how it's doing. Right there. So here you can see athlete league, and then it's replaced with unique identifier. So athlete team, team league, athlete league. You can see the weight is actually increased a little for this rule. And for the next rule, this is team and city. And actually, in our training set, we don't actually see this triple, I believe. So in the training set, we're not going to change this from the value that we specified as the initial value. But now let's look at our training and testing have finished. But let's quickly look at what happened to those rules. So weight learning finished, and we got these weights for our two rules. And you'll see when we actually run inference with the test data, we actually see that it grounds a number of these. So it grounds 24 instances of our rule for athletes and leagues and 59 instances for teams and cities. So maybe we've done better on roughly 83 facts. So let's run our test output. And so you'll see that if you remember before, the AUC overall was 9048, and now it's 9066. So we've got a bit of an improvement in the AUC, and the F1 seems to be about the same. Part of the reason is just that this improved the relation AUC, but we have many categories or labeled facts in the data set, so it didn't really help our category AUC. But you can see how by making these, by adding these new rules, we get some small improvements, and you could imagine that we could come up with a large set of these really complex rules and come up with a very rich knowledge graph identification model that has all of these features amongst the facts. There's one more data set that we discussed in our ISWC paper that uses linked brains data from music brains, and this has the exact same structure. You run fetch dataset, you compile the model, you run the load data, run KGI scripts, and then there's a different command for evaluation, which we specify in the README for music brains, just because the file names are different for the test data. So this is another one that takes a little while because it's lazy. So if you have the time or you're interested, you can run this on your own. So that's a demo of the knowledge graph identification code that we have on GitHub. It shows you some advanced features of PSL and a very complex example with many rules, many different partitions, weight learning. So hopefully this makes it easier if you're trying to write another complex model. And if you have any questions, feel free to post them on this channel or email the PSL user group. Great, thank you.